4.367 light-years away, something is glowing where nothing should be. The James Webb Space Telescope caught it on camera. Then it vanished. Now it is predicted to come back on a specific date at a specific spot in the sky around the nearest sun-like star to our own. If it shows up, we just found the closest planet humanity has ever directly seen with its eyes. The date is August of 2026. The clock is running. If you're new here, hit like and subscribe. Pour yourself something warm and get comfortable, because tonight I am walking you through exactly what Webb saw, why it matters, and why 16 months from now could change everything about the possibilities of interstellar travel. Now, let's ease into it. Part 1. The claim that changes everything. There is a pixel of light sitting in the data from the most powerful space telescope humanity has ever built, and it should not be there. Not because someone made a mistake, not because the equipment malfunctioned. It should not be there because finding it would mean something so extraordinary, so quietly earth-shattering, that the scientists who found it spent months checking their own work before they would even whisper about it publicly. A single faint point of thermal emission, hovering 4.367 light-years from where you're sitting right now, next to the nearest sun-like star in the entire galaxy, and if it is what it appears to be, it changes the answer to one of the oldest questions our species has ever asked. Are we alone in the neighbourhood? Let me set the scene for you. It is August 2024. The James Webb Space Telescope is parked about 1.5 million kilometres from Earth, orbiting a gravitational balance point called L2, where the Sun and Earth's pulls cancel out perfectly, giving it an unobstructed view of the entire universe. Webb has been doing extraordinary things since it came online, peering at galaxies from the first few 100 million years after the Big Bang, dissecting the atmospheres of distant worlds, imaging star nurseries in resolutions that make the old Hubble pictures look like watercolours. It is doing all of that. But on this particular occasion, Webb is not looking outward into the ancient universe. It is looking sideways, essentially, at something absurdly close by cosmic standards. It is staring at Alpha Centauri A. The team running the observation has activated a specialised instrument, a coronagraph, which is essentially a precise mask designed to block out the blinding light of the star itself, the same way you might hold your thumb up against the sun to see something faint nearby. And then they wait. 45 minutes of exposure at a time, patient, meticulous, letting photons accumulate on the detector. This is not a quick glance. This is the telescope equivalent of holding perfectly still in a completely dark room, waiting for your eyes to adjust until you can see something so faint it barely exists. And in that accumulated data, something appears. A faint point source. Thermal emission. The team labels it S1, Candidate Source 1, because in science you do not name things you're not sure about. And here is the thing that makes this moment unlike almost any other in recent astronomical history. This is not a planet inferred from a star wobbling slightly. It is not a transit signal detected from a dip in starlight. This is a direct observation of a thermal signature sitting in space next to Alpha Centauri A, the nearest sun-like star to our own sun. Let that land for a moment. 4.367 light-years. That is approximately 41 trillion kilometres. It sounds impossibly far, and by any practical human measure it is. No spacecraft we have ever built could get there in less than tens of thousands of years at conventional speeds. But on the scale of a galaxy that is 100,000 light-years across, 4.367 light-years is essentially the house next door. Alpha Centauri A is not some red dwarf squinting dimly at the edge of detectability. It is a G-type star, like our Sun. Slightly larger, slightly more luminous, similar temperature, similar age. If you swapped our Sun for Alpha Centauri A, you might not notice immediately. The sky would look almost the same, and yet, for all of that proximity, we have never been able to directly see what orbits it. Because directly imaging a planet next to a star is almost impossibly hard. The contrast ratio between a star and a planet, the difference in brightness, is roughly 10 billion to 1. Asking a telescope to find a planet next to a star is like standing in London and trying to spot a lit match held up next to a lighthouse in New York. That is not an exaggeration. That is roughly the scale of the problem. So when a faint signal appears in the data next to Alpha Centauri A, at a position consistent with a planet-sized object, at about 2 astronomical units from the star, 2 times the Earth-Sun distance, the team does not celebrate. They do not hold a press conference. They keep working. They check and check and check again, and then they schedule a follow-up observation. And here is where the story gets genuinely strange. Here is where it turns from a detection story into something more like a mystery. Because when they go back to look, S1 is gone. We're going to get to that. But before we do, I need you to understand one critical thing about what we are watching unfold here. This is not a story about a discovery that has already happened. This is a story about a test that is currently running. There is a prediction on the table, a specific, falsifiable, scientifically rigorous prediction that says S1 should reappear in a specific location in August 2026. Not maybe, not roughly. A precise prediction from orbital mechanics. And when that moment arrives, either the signal comes back in exactly the right place, or it does not. There is no middle ground, no wiggle room. August 2026 is the moment this candidate either becomes the nearest directly imaged exoplanet in human history, or quietly joins a long list of Alpha Centauri false alarms stretching back more than a decade. We are watching the clock tick down in real time, and I think you should know exactly what is at stake. Part 2. Seeing the Invisible. To understand why finding S1 matters so much, you first need to appreciate just how hard what JWST is attempting actually is. Because the telescope is not simply pointing a camera at Alpha Centauri A and snapping a picture. What it is doing is far more technically demanding and far more prone to error than that description implies. The fundamental problem with finding a planet next to a star is light. Specifically, the overwhelming, detector-saturating, signal-burying flood of light coming from the star itself. A star like Alpha Centauri A is not just bright, it is incomprehensibly brighter than anything orbiting it. In visible light, the brightness difference between a star and a Jupiter-sized planet next to it is around 10 billion times. 10 billion. If you tried to photograph both in the same image at the same exposure setting, the star would blow out the detector so completely that the planet's light would be completely invisible, drowned in the glare the way a candle flame is invisible when you hold it up next to the sun. This is the problem coronagraphy was invented to solve. A coronagraph is a mask, an extremely precise optical mask placed inside the telescope that physically blocks the light from the star before it reaches the detector. The concept was originally developed to study the sun's outer atmosphere, the corona, which is normally invisible because the solar disk is so much brighter. In a coronagraph, you essentially remove the disk and let the corona become visible. The same principle applies here. Remove the star and see what remains around it. But it is nowhere near as simple as it sounds. Alpha Centauri A is not a distant, faint star. It is the third brightest star system in the entire night sky as seen from Earth. It is so intrinsically bright that even after the coronagraph blocks the central disk, scattered light leaks around the edges of the mask. The diffraction pattern, the way light bends around the edges of apertures, creates a structured halo of residual starlight on the detector. This halo is not random noise. It has a pattern. And that pattern can look, in places disturbingly, like a faint point source, like for example, a planet. This is why the team is using JWST's MIRI instrument, the mid-infrared instrument, rather than a visible light camera. MIRI observes at 15.5 microns, which is deep in the thermal infrared. At this wavelength, a warm gas giant does not just reflect starlight, it actually glows. A planet in the Saturn to Jupiter mass range, sitting a couple of astronomical units from a sun-like star, would have a surface temperature somewhere around 200 Kelvin, which is cold by human standards but warm enough to radiate thermally in the mid-infrared. So Miri is looking for heat, not for reflected light. The planet, if it exists, is genuinely shining, faintly but detectably, at this wavelength. That changes the detection physics significantly. Thermal emission does not depend on being in the right geometry relative to the star. A planet glowing in infrared is visible from almost any angle. It also means that the contrast ratio, the brightness difference between star and planet, is somewhat more favourable in the mid-infrared than in visible light, because stars are not as overwhelmingly dominant in this wavelength range. You're comparing a star's thermal emission against a planet's thermal emission, rather than comparing a star's optical brilliance against a planet's dimly reflected light. The gap is still enormous, but it is slightly less impossible. Even so, what remains after the coronagraph is not a clean image. It is a residual mess of structured noise, the diffraction halo I described, combined with electronic noise from the detector, thermal fluctuations in the telescope structure, and the subtle but non-zero contribution of scattered light from Alpha Centauri B, which we will get to in detail later because that second star creates its own special category of problems. To extract a planetary signal from this mess, the team uses a technique called PCA-KLIP, Principal Component Analysis, Kahunen-Loew Image Processing. You do not need to memorize that name. What you need to understand is what it does. Imagine you have a photograph with a repeating pattern of static overlaid on it, like an old television screen with bad reception. The static has a structure, a characteristic fingerprint. If you can model that fingerprint precisely enough, you can subtract it from the image and see what is underneath. KLIP does this for the structured light pattern left by the star after the coronagraph blocks its centre. It uses multiple reference observations to build a mathematical model of what the stellar point spread function, the halo pattern, looks like, and then subtracts that model from the science data. What remains, in theory, is only things that are not part of the star's light pattern. Real point sources, real objects, in theory. The critical word, the word that keeps the astronomers who built this technique awake at night, is subtraction. Because subtraction of imperfect models from real data always leaves residuals, and residuals can look like anything. They can look like background galaxies, they can look like instrument artifacts, and yes, they can look like planets. The history of exoplanet science, particularly at Alpha Centauri, is littered with signals that survived preliminary analysis and turned out to be nothing. The detection of S1 sits, at this moment, right on the razor's edge between the real and the illusory. And to understand why that matters, you need to understand what has happened every single time before when someone thought they found something here. Part 3. The signal. So let us talk about what the data actually shows. Because even before we get to the history of false alarms or the disappearance or the August 2026 prediction, there is something here that genuinely demands your attention. This is not a marginal, barely there whisper in the noise. The numbers are real numbers, from a real instrument, on the most capable space telescope ever launched, and they are interesting. S1 appears as a point source at a separation of approximately 1.5 arcseconds from Alpha Centauri A. Now, 1.5 arcseconds sounds like nothing. It is a tiny fraction of a degree. But translated into physical distance at the known distance of Alpha Centauri, 1.5 arcseconds corresponds to roughly 2 astronomical units. 2 astronomical units. That means S1, if it is a real object, is sitting at about twice the Earth-Sun distance from Alpha Centauri A. To put that in perspective, 2 astronomical units puts it between the orbits of Mars and Jupiter in our solar system. It is sitting right at the outer edge of what we would call a temperate orbital distance from a Sun-like star. The flux, the brightness, of S1 at 15.5 microns is measured at approximately 3.5 millijanskys. A millijansky is an extremely small unit of brightness, but the number itself matters less than what you can infer from it. From that flux measurement, combined with the known distance to the system and some modelling of how warm objects radiate in the mid-infrared, you can work backward to an approximate temperature. The team estimates a characteristic temperature for S1 of around 225 Kelvin. 225 Kelvin is minus 48 degrees Celsius. To us, that is bitterly cold. But for a planet, that temperature is telling. A gas giant in the outer part of a planetary system around a sun-like star would be expected to have a temperature in roughly this range, depending on how much heat it retains from its formation and how much it receives from the star. Jupiter in our solar system has an effective temperature of about 128 Kelvin. Saturn is around 95 Kelvin. A more massive gas giant sitting at 2 astronomical units from a star slightly more luminous than our Sun, sitting at a temperature of 225 Kelvin, is completely consistent with an object in the Saturn to Jupiter mass range, perhaps on the larger side. The team's mass estimate runs from roughly 90 to 150 Earth masses. For reference, Saturn is about 95 Earth masses. Jupiter is about 318 Earth masses, so S1, if real, sits right in that range, Saturn mass to roughly half Jupiter mass. And here is something interesting about gas giants in this mass range. They are all roughly the same size. This sounds counterintuitive. Surely a heavier gas giant would be bigger. But above a certain mass threshold, the additional gravity compresses the gas faster than the planet grows in radius. The result is that objects from Saturn up to several times Jupiter's mass all have radii within a factor of roughly 1.5 of each other, all approximately Jupiter-sized. So regardless of where S1 falls within that 90 to 150 Earth mass range, we are probably looking at a planet about the size of Jupiter. Now comes the question you're absolutely entitled to ask. How confident is the detection? The signal-to-noise ratio of S1, the comparison between the brightness of the signal and the level of background noise, falls between 4 and 6, depending on exactly which analysis method you use. Translated into statistical confidence, that is approximately 3.3 to 4.3 sigma. In particle physics, the gold standard for a confirmed discovery is 5 sigma. 5 sigma means the probability of the signal being a random fluctuation, pure noise accidentally mimicking a real object, is less than 1 in 3.5 million. At 3.3 to 4.3 sigma, the probability of a false positive is higher. Not frighteningly high, we're still talking about something in the range of 1 in several thousand to 1 in tens of thousands, depending on the exact value, but high enough that a careful scientist will not call it a confirmed detection, high enough that the team correctly labels it a candidate, high enough that you should feel a genuine tension when I tell you about what happened when they tried to observe it again, and that tension is exactly the right feeling to have right now. Because what the data shows is a signal that is almost certainly not nothing, and almost certainly not yet proven to be something. It occupies that uncomfortable middle space where the universe is being deliberately, frustratingly non-committal. And it is about to get stranger. Part 4. The Disappearance. February 2025. The team returns to Alpha Centauri A with the same instrument, the same wavelength, the same coronagraph configuration. The observation runs, the data comes in, the KLIP processing runs, and where S1 was sitting 6 months earlier, or rather where it should be if it were stationary, which a real planet would not be, there is nothing. Below the detection threshold, absent, April 2025. Another look, same result, nothing. Now, I want to be careful here about how we read this disappearance, because the first instinct, the instinct shaped by the Alpha Centauri history we are going to get to shortly, is to hear it disappeared and immediately conclude it was never real. And that instinct is understandable. The graveyard of Alpha Centauri false positives is well documented, and we have been burned before. But the disappearance of S1 in context is not actually evidence against it being real. Here is why. A real planet does not stay in one place. It orbits, and an orbit is not a circle of uniform detectability. The sensitivity map of JWST's coronagraphic observations of Alpha Centauri A, the map of which positions on the sky can be detected at what confidence level is highly uneven. Near the centre of the coronagraph mask, sensitivity drops sharply because the star's residual scattered light is strongest there. In certain angular directions from the star, the light from Alpha Centauri B contributes additional noise. The result is that there are regions in the image plane around Alpha Centauri A where a real planet would be detectable, and regions where the same planet, at the same brightness, would be undetectable, buried in noise. If S1 is on an eccentric orbit, and the modelling strongly suggests it is, then as it moves through its orbit, it will periodically sweep through these low sensitivity regions and effectively vanish from JWST's detectable field, not because it has stopped existing, but because the telescope cannot see it through the noise. Think of it like trying to track a fish in murky water. Sometimes it swims into a clear patch and you can see it perfectly. Then it drifts into a darker region and disappears, not because the fish is gone, but because your ability to see it has changed. The team ran millions of orbital simulations, literally millions, testing which orbital configurations are consistent with the following observed facts. S1 is visible at its August 2024 position. S1 is not visible in February 2025. S1 is not visible in April 2025. The simulations converged on a family of eccentric orbits, with eccentricities around 0.4, semi-major axes between roughly 1 and 2 astronomical units, and orbital inclinations around 50 to 130 degrees. These are not wild, exotic orbits. Eccentric orbits are common in planetary systems, particularly ones that have undergone gravitational scattering events. More on that later. More importantly, the simulations produce a prediction, not a vague hope, an actual, specific, testable orbital mechanics-based prediction. Given the orbital parameters consistent with the August 2024 detection and the 2 non-detections, S1 should move back into JWST's sensitive detection zone in approximately August 2026. The predicted position is specific enough to verify. If the signal reappears, in roughly the right place, at roughly the right brightness, at roughly the right time, that is not coincidence. That is confirmation. So what we are watching right now, in real time, is the interval between a candidate detection and its definitive test. The clock is running. The question is on the table. Did we see a planet, or did we see a warm artifact of imperfect starlight subtraction that happened to sit in exactly the right position at exactly the right brightness to fool us? We have had that happen before, right here, around this very star. And the story of how that went is something you need to know before you decide how much hope to invest in August 2026. Part 5, the 2012 illusion. Before S1, before JWST, before coronagraphy of Alpha Centauri was even technically feasible, there was a moment in 2012 that felt, briefly, like the answer had already arrived. A team of researchers, analysing radial velocity data, the method that detects planets by watching a star wobble microscopically toward and away from us as an orbiting planet tugs on it gravitationally, announced the detection of a planet around Alpha Centauri B. They called it Alpha Centauri BB, Earth mass, extremely close in orbit, just a few days long, the nearest exoplanet ever found, the nearest world beyond our solar system. The scientific community was cautious but excited. The popular press was considerably less cautious. Here was, potentially, a world next door, a planet orbiting the second star of the nearest star system. Radio signals travel at the speed of light. A broadcast aimed at Alpha Centauri would arrive in 4 1/3 years. If there were beings there and nobody was claiming Earth mass close-in planets are habitable, but still, we could theoretically be in a slow conversation with them within a human lifetime. It felt enormous. And then the years passed. Other teams tried to reproduce the detection. The signal had an amplitude of about 0.5 meters per second. The planet was supposedly causing Alpha Centauri B to wobble at about 0.5 meter per second, roughly walking pace. That is an extraordinarily small signal, and when researchers dug into the data analysis more carefully, they found something uncomfortable. The signal was real, it was genuinely present in the data, but it appeared to be an artifact, not a planet. A pattern introduced by the way the data had been sampled over time, interacting with the analysis window used to extract it. The sampling cadence of the observations had essentially created a ghost, a frequency pattern that mimicked a planetary signal but was generated entirely by the data collection process itself. By around 2015, the consensus had shifted. Alpha Centauri BB was almost certainly not real, not a failed detection, not an unconfirmable signal, a mathematical artifact that had been mistaken for a world. The emotional fallout was real. Scientists who had built careers on this detection, who had planned follow-up studies, who had attached their reputations to the result, they had to reckon with the possibility that the universe had not cooperated. And that lesson, that specific, painful, Alpha Centauri-specific lesson, is precisely the atmosphere into which S1 has now been detected. Every person who has looked at the S1 data knows this history. Every reviewer who has read the paper knows this history. The bar for Alpha Centauri is not the standard astronomical bar. It is higher. Because this system has fooled us before, badly and publicly. Which is exactly why the approach being taken with S1, direct imaging, orbital prediction, falsifiable reappearance test, represents something genuinely different. Not just methodologically different, philosophically different. For the first time, a potential planet claim around Alpha Centauri comes with a scheduled expiration date for ambiguity. Part 6. Ghosts in the Data. The story of Alpha Centauri BB is not a story about incompetent scientists. It is a story about how extraordinarily subtle the sources of false signals in astrophysical data can be. And understanding this matters for how we interpret S1, because the question of whether S1 is real or artifactual is genuinely open, and the mechanisms that could produce a false signal are real and documented. In radial velocity work, a phenomenon called a window function creates exactly this kind of ghost. When you observe a star on a schedule, say, once every few nights, subject to weather and telescope availability, the gaps and cadences in your observations form a pattern. That pattern has its own frequency structure. When you apply a Fourier analysis to your data to search for periodic signals, the window function interacts with the analysis and can produce spurious peaks at frequencies that correspond to no real planet whatsoever. The sampling artifact essentially manufactures a signal. This is not exotic or unusual. It is a known hazard that good data analysts actively look for. But it is subtle enough that it fooled a competent team in 2012 and made it into a peer-reviewed paper and onto the front pages of science news sites worldwide before the problem was identified. In chronographic imaging, the analogous risks involve the structure of the point spread function residuals, the leftover starlight pattern after KLIP processing, which can create structures at certain positions and brightness levels that are indistinguishable, in a single epoch, from a real faint companion. The risk is that one well-placed PSF residual could sit, at one moment, exactly where a planet would be expected, and then disappear in subsequent observations simply because the observing geometry or thermal state of the telescope changed slightly and the residual pattern shifted. S1 does not reappear in 2 follow-up observations. Is that because the planet moved into a low sensitivity zone, as the orbital model suggests? Or is it because the first detection was a PSF artifact that happened to be at that location on that night, and then resolved differently when conditions changed? This is the question. This is the unresolved, honest, nobody knows yet question that August 2026 will answer. Part 7. The Pattern of False Hope. Alpha Centauri. BB is not the only ghost in this neighbourhood. Proxima Centauri, the third member of the Alpha Centauri system, a small red dwarf that is actually the closest star to our Sun, at about 4.24 light-years, has its own complicated detection history. Proxima b, a potentially rocky world in the habitable zone of Proxima Centauri, was detected in 2016 and is generally considered a robust detection, It has survived multiple independent confirmations. But then came Proxima c, claimed in 2019, an alleged super-Earth on a longer orbit, detected via radial velocity with an even more marginal signal. Subsequent analyses have been deeply divided. Some teams confirm it, others find the signal consistent with stellar activity rather than a planet. As of the mid-2020s, Proxima c remains unconfirmed and contested. Notice the timeline. 2012, Alpha Centauri B, ultimately found to be spurious. 2016, Proxima b confirmed. 2019, Proxima c still contested. The pattern across this system is a cycle of announcement, excitement, scrutiny, and doubt, with occasional genuine confirmations interspersed among the noise. Scientists who work on this system have developed a particular kind of calibrated skepticism, not cynicism, but hard-won precision about what constitutes real evidence. They have seen too many Alpha Centauri mornings that turned out to be false dawns, and yet here is what makes S1 different from every single one of these previous claims. The others were all detected, assessed, questioned, and left in a state of permanent ambiguity. There was no scheduled moment at which the question would definitively resolve. Alpha Centauri B is still, in some technical sense, unconfirmed, rather than refuted. It just faded into the background as interest dropped, and the evidence against it accumulated without ever delivering a final verdict. Proxima c may spend decades in that same limbo. But S1 has a date, a specific calendar date by which it should either confirm or fail, and that is a fundamentally new kind of claim. For the first time in the troubled history of planetary detection, around our nearest stellar neighbours, we have a real deadline. August 2026. Mark it. Part 8. Why this time might be different. So let us be precise about why the S1 detection approach is methodologically distinct from everything that came before it. Because it would be easy to dismiss this as just another Alpha Centauri hopeful, and I do not think that dismissal would be fair or accurate. The previous false positive, Alpha Centauri B, was a radial velocity detection. Radial velocity works by measuring the Doppler shift of a star's spectral lines, the tiny change in frequency as the star moves toward or away from us. It is an indirect method. The planet is never seen. Its existence is inferred from its gravitational effect on the star. An inference is always vulnerable to alternative explanations. If something else, stellar oscillations, magnetic activity cycles, data artifacts, can produce the same pattern in the data, you cannot distinguish a real planet from that imposter without extraordinary care. 2012 showed exactly how that can go wrong. Direct imaging is different in a fundamental way. In direct imaging, you are not inferring the planet from an effect on the star. You are observing the planet itself, or at least you are observing a source of photons that is physically located away from the star at a specific position in space. The photons from S1 are coming from a specific angular separation and position angle relative to Alpha Centauri A. They exist. The question is only whether they are coming from a planet or from a residual artifact of the data reduction process. But crucially, a PSF artifact is not going to orbit. It is not going to reappear at a predicted orbital position 2 years later. If S1 comes back in August 2026 at the position the orbital models predict, it will have demonstrated behaviour that no data processing artifact can mimic. Because data processing artifacts do not follow Kepler's laws, that is the key insight. The prediction is not just about whether the signal reappears, it is about whether it reappears where orbital mechanics says it should. That specificity is what transforms S1 from an interesting detection into a scientific test. And the fact that the prediction was made before the confirmation, not retrofitted afterward, is what gives it genuine evidential weight. There is also the question of independent verification. If S1 is confirmed by JWST in August 2026, it immediately becomes a target for every major observatory on Earth and in space. The extremely large telescope currently under construction in Chile, will have a primary mirror 39 meters across, larger than a 5-story building, and coronagraphic capabilities that exceed anything currently operational. JWST can detect S1 in the thermal infrared. ELT could potentially observe it at other wavelengths. Gaia, the ESA astrometry satellite, has been precisely tracking the position of Alpha Centauri A for years, and if a gas giant is tugging on that star, the astrometric wobble should eventually become detectable in Gaia's data, an independent confirmation via a completely different method. The scenario where S1 is confirmed is not a scenario where one telescope said it once and everyone believed. It is a scenario where multiple independent methods, each with completely different systematic errors, converge on the same object. That convergence is what confirmation looks like in modern science, and the architecture for that convergence is already in place, waiting for August 2026 to pull the trigger. Part 9. 3 Suns. To understand why finding a planet around Alpha Centauri A is both so compelling and so complicated, you need to understand the system it would have to exist within. Because Alpha Centauri is not a single star. It is a family of 3, and the dynamics of that family create a gravitational environment unlike anything in our own solar system. Alpha Centauri A is the largest member, a G-type star like our Sun but about 10% more massive and 20% larger. It is slightly older than our Sun, approximately 5 billion years compared to 4.6 for ours, and a bit more luminous, putting out about 50% more energy. If you replaced our Sun with Alpha Centauri A and kept everything else the same, Earth would actually be a bit too warm. You would need to be sitting at roughly 1.2 to 1.3 astronomical units for the same flux our planet receives. But it is fundamentally recognizable as a Sun-like star. Alpha Centauri B is the second star, an orange K-type dwarf, smaller and dimmer than A, with about 90% of the Sun's mass and roughly half its luminosity. It orbits Alpha Centauri A in a highly elliptical orbit that brings the two stars as close as 11 astronomical units at their nearest approach, closer than Saturn is to our Sun, and as far as 36 astronomical units at their most distant, about as far as Neptune. Their orbital period together is approximately 79.9 years. Right now, in the mid-2020s, A and B are in a relatively wide phase of their orbit, separated by more than 20 astronomical units. That matters enormously for our story, and we will return to it. Proxima Centauri is the third member, a small red M-type dwarf star located about 13,000 astronomical units, 0.2 light-years, from the AB pair. Whether Proxima is gravitationally bound to A and B has been debated, but current measurements of its velocity and trajectory are consistent with a very wide-bound orbit around the AB centre of mass, though the orbit would be immensely long, possibly millions of years. Proxima is the closest of the 3 to us, at 4.24 light-years versus 4.37 for A and B. This is the gravitational environment into which S1 would have to have formed and survived. A gas giant candidate sitting at 1 to 2 astronomical units from Alpha Centauri A, in a system where another star the size of Saturn's orbit swings through the neighbourhood every 80 years. The fact that a stable planetary orbit could even exist in this region has been studied extensively, and the answer is that yes, it can, provided the planet is on a reasonably low inclination prograde orbit that keeps it well within the gravitational sphere of influence of A. But the history of how such a planet would have formed and survived almost certainly involves the kind of dynamical violence that leaves marks, and those marks are visible in S1's orbital properties. Part 10. A sky with multiple shadows. Here is something to consider while we talk about the mechanics of this system. Imagine you're standing on the surface of a moon orbiting S1. We will get to whether that is even conceivable in a later chapter, but just let yourself be there for a moment. Look up. Alpha Centauri. A hangs in the sky, slightly larger and slightly brighter than our Sun appears from Earth, filling your sky with warm yellowish light. Your shadow falls sharp and clear on the ground in front of you. But there is another shadow, slightly softer, offset by an angle that changes over months and years as the two stars orbit each other. Alpha Centauri B, the orange companion, is currently sitting about 20 astronomical units from A, too distant to be overwhelming, but bright enough from this vantage point to be clearly a disk, not a point. Not like a second sun in terms of raw energy, but unmistakably solar. Something in between a sun and a very bright moon. A presence you could read by, and it casts its own shadow, faint but real, soft-edged, doubled against every object on the surface. Turn around and look toward the horizon. There, in a sky that is otherwise brilliant with stars, one point burns a distinctly reddish colour. Not bright enough to be dramatic, but too bright and too red to ignore. That is Proxima. The distant third member of this system, 50 times too faint to be a second sun, but close enough to resolve as a slightly reddish point rather than blending into the stellar background. It is there every night, a constant companion on the horizon of your alien sky. That sky, with its three stellar presences of completely different character, casting multiple overlapping shadows, is the sky that might exist around S1 right now, 4.367 light-years from where you are sitting, and whether it is inhabited by anything that could look up at it is a question we are not close to answering. But the first step to answering it, the prerequisite to any further question, is confirming that the world itself is real. Which is why August 2026 is not just an astronomical observation, it is the opening of a door. Part 11. The binary problem. Now let me tell you about the problem that makes all of this so technically difficult, because it is directly connected to both the detection of S1 and its subsequent disappearance. And if you're going to understand why the August 2026 test is so critical, you need to understand what the telescope is actually fighting against every time it tries to observe this system. Alpha Centauri A and B orbit each other. Currently, in the mid-2020s, they are separated by more than 20 astronomical units as seen from their mutual centre of mass. But from our perspective here on Earth, their angular separation on the sky is several arc-seconds, a handful of times larger than the separation between S1 and Alpha Centauri A. What that means in practice is that when JWST points at Alpha Centauri A and opens up its coronagraph, Alpha Centauri B is sitting just outside the coronagraph mask, not blocked, not far away. Right there, just beyond the edge of the instrument's central obscuration, pouring its own light onto the detector. Alpha Centauri B is slightly less luminous than A, but it is not dim. Its light does not simply fall on a different part of the detector and stay there. Light does not work that way. Because of diffraction, the way light waves bend around edges and obstacles, B's light spreads out from its central image position in a structured halo called a point spread function. That PSF from B overlaps with the region of the detector where faint objects orbiting A might be found. It contributes to the noise floor. It creates a spatially structured background on top of which you are trying to detect S1's tiny signal. This contamination from B is not constant. It varies with the exact angular separation between A and B on the sky, which changes as the two stars orbit each other. It varies with the position angle, the direction from A to B, which also shifts as the orbit progresses. And it varies with small differences in the pointing and thermal state of the telescope between observations. The result is a noise field that changes from epoch to epoch. The residual pattern left after KLIP processing looks slightly different every time you observe, because the structure you're trying to subtract, dominated partly by A's PSF but contaminated by B's PSF, is never exactly the same twice. This is why having a planet appear in one epoch and disappear in two subsequent epochs is not automatically fatal to the hypothesis. The noise field itself is shifting. A signal sitting close to the detection threshold could be visible in one configuration and buried below it in another, simply due to changes in the contamination geometry. The orbital motion hypothesis, which says S1 moved into a lower sensitivity region, is reinforced by the fact that the lower sensitivity regions of the detector are themselves partly determined by where B's contamination is worst. S1, moving along its orbit, could quite naturally drift from a region of relatively clean sky into a region where B's noise is higher and drop below detectability without any change in its intrinsic brightness. This is also why the timing of the current observations is so lucky, and why the window may not last. Right now, A and B are in their widest separation phase. Their orbital period is roughly 80 years. The current wide separation window will not last indefinitely. As the years go on, A and B will gradually begin to close their separation again, returning eventually to their closest approach of 11 astronomical units, close enough that the contamination problem becomes dramatically worse. The current period, the 2020s and into the early 2030s, represents a precious window of relative clarity. The contamination from B is manageable. The coronographic observations are challenging but feasible. JWST is operating during exactly the right phase of A and B's 80-year orbital waltz to make this detection attempt possible at all, and if we miss it, we might not get another chance with comparable technology for decades. Part 12. The observation window. There is a concept in astrophysics called an observation window, a period of time during which a specific measurement is possible or optimal that would otherwise be impossible or severely degraded. The discovery of gravitational waves from merging black holes, for example, requires the merger to actually happen during your operational period. The first images of a black hole required the Event Horizon Telescope to achieve global interferometric baseline in the right era of technology. These things do not wait around indefinitely. The observation of S1 around Alpha Centauri A is a window in exactly this sense, and it is operating on two different timescales simultaneously. The first is the orbital period of A and B, the roughly 80 years it takes them to complete one orbit around their common centre of mass. The last closest approach was in 2016. The next widest separation period, when contamination from B is lowest, is now, and it will gradually degrade as the pair begin to close again over the coming decades. We have perhaps 2 more decades before contamination from B makes coronographic imaging as difficult as it was before the current separation. This is the long window. The short window is JWST's operational lifetime. Webb was launched in December 2021, and its fuel budget, the propellant used to maintain its orbit at L2 and periodically adjust its position, was sufficient for a minimum 10-year mission, with optimistic estimates suggesting 20 years or more. But every spacecraft eventually reaches end of life. At some point, Webb will run low on fuel, or a critical component will fail, and the era of JWST science will close. There is no guarantee it operates until the mid-2040s, when A and B will have closed their separation enough to make current observations difficult. Right now, in the middle of the 2020s, both windows are open simultaneously. JWST is operational and performing better than expected. A and B are in their widest separation in decades. The coronographic mode is working. S1 was detected, or at least a candidate consistent with a planet was detected. And there is a prediction, a specific, testable, orbital mechanics prediction that says the candidate should become visible again in August 2026. This is not a random moment. This is a convergence. Technology, timing, orbital geometry, and scientific preparation have all aligned to create a window that almost certainly does not exist again within the next several decades in this exact combination. What happens in August 2026, whether the signal comes back or stays dark, will be one of the most consequential single moments in the history of our attempt to understand whether our solar system is unique or typical, whether worlds like ours are common or rare, whether the nearest star system is barren or inhabited by planets that might, in some distant future, be destinations rather than points of light. And that possibility, the idea of a destination, starts with understanding exactly what S1 might be. Part 13. The orbit. Let us talk about what the orbital modelling actually tells us about S1's path through space, because the orbital parameters are not just useful for predicting reappearance. They paint a picture of what kind of world this might be, how it moves through the system, and what its relationship to the habitable zone looks like. The best fit orbital models from the simulations give Swan a semi-major axis, the average orbital radius, of somewhere between 1 and 2 astronomical units. The uncertainty spans that range because the detection history is limited. 1 confirmed epoch, 2 non-detections. With only those 3 data points, you cannot pin down the orbit with the precision you would have after, say, a full orbital period of observations. What you can do is constrain the family of orbits consistent with the data, and that family converges on a semi-major axis of roughly 1 to 2 astronomical units. For comparison, Earth orbits at 1 astronomical unit, Mars at 1.5. The main asteroid belt is centered at about 2.2 astronomical units. So S1 is sitting in a belt of orbital space that is deeply familiar from our own solar system, inner to middle range, well within what we would call the terrestrial and inner gas giant zone. The eccentricity is estimated at around 0.4. An eccentricity of 0 means a perfectly circular orbit. The planet always stays the same distance from the star. An eccentricity of 0.4 means the orbit is noticeably elongated, like a stretched ellipse. At its closest approach to Alpha Centauri A, what is called periastron, S1 would be somewhere around 0.6 to 1.2 astronomical units from the star. At its most distant point, apastron, it would be sitting at about 1.4 to 2.8 astronomical units. To translate that into energy terms, a planet on an eccentric orbit like this experiences dramatically different levels of stellar radiation at different points in its orbit. Near periastron, S1 receives significantly more energy from Alpha Centauri A, potentially comparable to what Earth receives from the Sun, or even somewhat more. Near apastron, it receives much less, more like what the outer edge of Mars's orbit receives. This swing in irradiation over a single orbit is roughly a factor of 5. For S1 itself, a gas giant with no solid surface, this just means its upper atmosphere is warmer near periastron and cooler near apastron. But for any moon orbiting it, and we will get to moons, this creates a climate of dramatic seasonal extremes. The orbital inclination estimated from the model sits around 50 degrees, or alternatively around 130 degrees. The two solutions are mathematically degenerate with the available data, meaning you cannot distinguish between them yet. An inclination of 50 degrees means the orbit is tilted about 50 degrees relative to the plane of the sky as we see it. An inclination of 130 degrees would mean the orbit is retrograde. S1 would be orbiting in the opposite direction to whatever we define as forward for this system. Retrograde orbits are not impossible. Many moons in our solar system are retrograde, but they are less common for primary planets, and a retrograde gas giant would carry interesting implications about how the system formed. The orbital period, how long it takes S1 to complete one full orbit, works out to roughly 2 to 3 years for a semi-major axis in the 1 to 2 astronomical unit range. This is shorter than Mars's orbital period of 1.9 years, but in the same ballpark. It is long enough that a full orbital conformation, tracking S1 through enough of its orbit to precisely characterize all its parameters, will take years of follow-up observations after the initial reappearance. The August 2026 detection, if it happens, is the beginning of characterization, not the end of it. This orbit, eccentric, inclined, medium period, threading through the inner part of the Alpha Centauri A system, is entirely plausible for a gas giant. But it is also suggestive of history, and that history, written in the shape of the orbit itself, tells a story about what this system has been through. Part 14. A violent history. A gas giant on an eccentric orbit does not simply form that way. Planets form from a disk of gas and dust rotating around a young star, and the dynamics of that disk tend to produce planets on nearly circular orbits, the same reason the planets in our solar system all have low eccentricities, with Earth at 0.017 and even Mars only at 0.093. Gas disk interactions damp eccentricity. They smooth out the orbits, A freshly formed gas giant in a disk is almost always on a near circular path, so when you find a gas giant on an orbit with eccentricity 0.4, something happened after the disk dissipated. Something kicked it. And in planetary science, something kicked it almost always means gravitational scattering, the chaotic, violent process by which planets interact with each other gravitationally, exchanging energy and angular momentum in close encounters that can send one planet careening outward while boosting another inward, dramatically reshaping both orbits in the process. The evidence from our own solar system is strong that this kind of violence was the rule, not the exception, in the early history of planetary systems. The Grand-Tack hypothesis suggests that Jupiter and Saturn executed a complex dance of inward and outward migration during the first few million years of the solar system, reshaping the entire inner solar system in the process. The Late Heavy Bombardment, a period roughly 4 billion years ago when the inner solar system received an intense barrage of impactors, is thought to have been triggered by a reorganization of the giant planets' orbits. Planetary systems are not settled, calm places from the beginning. They are born in chaos and gradually relax into stability over hundreds of millions of years, if they reach stability at all. For S1, the eccentric orbit is a scar. It is evidence that something in this system was disrupted. Possibly there were multiple gas giants originally, a more compact, more populated inner system, and gravitational encounters between them pumped eccentricities, scattered some planets entirely out of the system, and left the survivor on the stretched inclined orbit we see today. The inclination of the orbit, 50 or 130 degrees, is particularly suggestive. In a dynamically quiet system, all the planets tend to share a common orbital plane inherited from the formation disk. A highly inclined orbit implies something tilted it, another planet, a close stellar encounter, possibly the gravitational influence of Alpha Centauri B during one of its closer passages. The binary companion is relevant here. During the phases of A and B's orbit when the two stars are at their closest, 11 astronomical units at periastron, the gravitational perturbations from B on any planets in A's inner system are not negligible. They are not strong enough to immediately eject a gas giant, but over millions of years of accumulated perturbations, they can pump eccentricities, tilt orbital planes, and destabilize configurations that would otherwise be stable. The eccentric inclined orbit of S1 may be in part the permanent record of 80-year periodic gravitational nudges from B accumulated over billions of years. This means S1 is not just a planet, it is a survivor. Whatever the original architecture of the Alpha Centauri system looked like, however many worlds formed around it in the early disk, S1 is what is left after billions of years of gravitational pruning by a stellar companion that comes calling every 80 years. That is not a comforting thought for habitability, but it is a fascinating one for understanding how planetary systems in binary star environments evolve. And it makes the Moon question, which is our next stop, both more complicated and more interesting. Part 15. A gas giant in the habitable zone. Let us talk about what S1's orbit actually means in terms of energy, specifically in terms of the habitable zone. The habitable zone around a star is the range of orbital distances at which a planet with a suitable atmosphere and sufficient surface pressure could theoretically maintain liquid water on its surface. It is not a guarantee of habitability. There are plenty of ways to be in the habitable zone and still be deeply inhospitable, but it is the first, most basic filter. Too close to the star and your water boils away, and your atmosphere strips off in a few 100 million years. Too far, and your water freezes permanently unless there is a subsurface ocean kept warm by internal radioactive heating or tidal forces. For Alpha Centauri A, with its roughly 50% higher luminosity than our Sun, the habitable zone shifts outward compared to our own. The inner edge sits at roughly 1.2 astronomical units. The outer edge extends to about 1.7 to 2 astronomical units, depending on which atmospheric model you use. The exact boundaries are debated, There are various definitions based on different assumptions about atmospheric composition and cloud feedback, but the general picture is clear. The habitable zone around Alpha Centauri A is centered at a bit more than 1 astronomical unit, and it spans roughly from 1.2 to 2 astronomical units. Now look at S1's orbit. Semi-major axis 1 to 2 astronomical units. Eccentricity 0.4. That means at periastron, S1 dips to somewhere around 0.6 to 1.2 astronomical units, inside or at the inner edge of the habitable zone. At apastron, it sits at roughly 1.4 to 2.8 astronomical units, squarely within or just beyond the outer edge of the habitable zone. Depending on the exact orbital parameters, S1 spends at least part of its orbit within the habitable zone of Alpha Centauri A. Does this mean S1 itself is habitable? Absolutely not. S1 is a gas giant. 90 to 150 Earth masses of hydrogen and helium, with no solid surface, enormous atmospheric pressure, powerful radiation belts from its magnetic field, and no place for liquid water to pool and chemistry to percolate. Whatever is going on inside the cloud tops of S1, it is not life as we understand it. The planet itself is not a candidate for biology. But the habitable zone matters for what might orbit it. Because gas giants have moons. Jupiter has 4 large moons, Io, Europa, Ganymede, and Callisto, and dozens of smaller ones. Saturn has Titan, with its thick nitrogen atmosphere and lakes of liquid methane, and Enceladus, with its subsurface ocean and geysers of water vapour. If a gas giant the size of S1 exists in the habitable zone of a Sun-like star, the question of whether it has large moons, and whether those moons could be habitable, becomes one of the most compelling scientific questions in astronomy. This is not fringe speculation. It is a subject of serious peer-reviewed research. The same factors that make large rocky moons possible in our outer solar system operate at least as strongly for a gas giant sitting in a star's habitable zone. And the conditions on such a moon might be extraordinary, so let us go there. Part 16. The Moon Hypothesis. The existence of large moons around gas giants is not unusual. In our solar system, Jupiter's moon Ganymede is larger than the planet Mercury. Saturn's Titan has a thicker atmosphere than Earth, and a complex organic chemistry that some researchers consider an analogue for early life precursor chemistry. Callisto is about the size of Mercury. These are not tiny, geologically dead rocks. These are worlds in their own right, each one interesting enough to have dedicated missions aimed at them. The question of whether gas giants in other star systems have large moons, what astronomers call exomoons, has been an active research area for years. The detection challenge is extreme. Exomoons are small compared to their host planets, and spotting one from 4 light-years away requires precision that even JWST cannot currently achieve for a routine detection. But theoretically, there is no reason exomoons cannot exist around gas giants in other systems, and if they exist around a gas giant in the habitable zone of a Sun-like star, the implications are significant. Researchers René Heller and Rory Barnes published detailed analyses of what they called habitable moons, a concept they made scientifically rigorous in papers around 2012 and onward. Their work showed that a moon orbiting a gas giant in the stellar habitable zone could receive energy from 3 sources simultaneously. First, reflected starlight from the gas giant itself, the giant planet bouncing stellar radiation back at the moon. Second, direct stellar radiation from the star, since the moon would be orbiting in the stellar habitable zone. Third, tidal heating. A large moon in a non-circular orbit around a massive gas giant would experience continuously shifting tidal forces as it moves closer and farther from the planet in its orbit. This tidal flexing generates heat in the moon's interior, the same process that drives the volcanically active surface of Jupiter's moon Io. For a moon around S1, this tidal heating could provide an additional heat source independent of stellar radiation, potentially enough to prevent freezing even when S1 is near a pastron and stellar flux is lower. The mass of a potentially habitable moon is worth considering. Scaling from our solar system, Moons tend to have masses roughly 1/10,000th of their host planet's mass. For us 1 at 100 Earth masses, that would suggest characteristic moon masses of roughly 100th of an Earth mass, moon-sized objects. That is on the small side for retaining a thick atmosphere over geological time. But these scaling relationships are derived from a single planetary system, a gas giant that formed in a dynamically active system, or one that captured a large moon during a close encounter with another planet early in the system's history, could easily host larger moons. Mars is about 1/10th of an Earth mass, and it retains a thin atmosphere. Earth's moon is about 1/81st of Earth's mass. A moon of S1 could plausibly be anywhere in that range, and a moon of Earth mass or larger, orbiting a gas giant in the habitable zone of a Sun-like star with the right atmospheric composition and sufficient internal heat, is not obviously uninhabitable. It would face challenges. S1's eccentric orbit means the Moon experiences wide swings in stellar flux. S1's powerful magnetic field would create intense radiation belts that could strip a Moon's atmosphere if the Moon lacks its own magnetic field. The tidal locking question, whether the Moon rotates synchronously with S1 or independently, matters for climate, as a tidally locked moon has a permanent day side and night side. These are not trivial problems, but they are not insuperable ones either. Europa is kept warm by tidal heating despite sitting outside the nominal habitable zone. Titan retains its thick atmosphere despite being tiny. Nature finds ways, and the question of whether a moon around S1 could find a way, could balance stellar flux, tidal heating, magnetic shielding, and atmospheric retention in a configuration that permits liquid water somewhere on its surface, is a question we cannot currently answer, but might one day be able to investigate. And the first step to ever investigating that question is confirming that S1 itself is real. Which brings us back, as always, to August 2026. Part 17, Life on a Moon. Let us be honest about what we know and what we do not know. When we talk about habitability of a hypothetical moon orbiting S1, we are stacking several layers of speculation on top of what is itself still a candidate detection. This is not bad science. It is legitimate scientific exploration, the careful, methodical working through of possibilities that allows us to know what questions to ask when the data does come in. But we should hold these ideas lightly. What we know is this: a moon large enough to retain liquid water on its surface requires several things to work together. First, it needs a source of energy. A moon at the right orbital distance from Alpha Centauri A would receive stellar radiation in the range of what Earth and Mars receive, between roughly 60 and 140% of Earth's solar flux, depending on where S1 is in its orbit. That is within the range where liquid water is physically possible on a body with an Earth-like atmosphere. The eccentricity introduces significant variation in that flux over the orbital period of 2 to 3 years, which is a challenge but not automatically fatal. We will return to that in the next section. Second, the Moon needs an atmosphere capable of sustaining appropriate surface temperatures and pressure. This requires a body massive enough to retain a gas envelope over geological time against atmospheric escape driven by stellar radiation. Earth retains its atmosphere because it is large enough and its gravity strong enough, and because its magnetic field deflects much of the solar wind that would otherwise erode atmospheric molecules. A moon of Mars mass, about 1/10th of Earth's mass, can retain a thin atmosphere, but struggles against intense ultraviolet radiation without magnetic protection. A moon of near-Earth mass would do considerably better. Third, and critically for the S1 scenario, the Moon needs protection from the radiation environment around the gas giant. Gas giants like Jupiter maintain intense radiation belts, regions of space filled with energetic charged particles trapped by the planet's magnetic field. Inside these belts, the radiation environment is lethal on short timescales for unprotected biology. Io sits just inside Jupiter's main radiation belt and receives enough ionizing radiation per day to kill a human many times over. Europa, slightly farther out, is still in a challenging radiation environment, though its subsurface ocean is shielded by its ice shell. A moon orbiting S1 would need to sit far enough from the gas giant to be outside the worst of its radiation belts, or it would need its own strong magnetic field to deflect the charged particles. Tidal heating deserves its own discussion here because it is genuinely remarkable as an energy source. Io produces more heat per square meter than any other body in the solar system, powered entirely by tidal flexing as it orbits inside Jupiter's powerful gravitational field. That same mechanism, scaled appropriately for a moon, at a different orbital distance from a more distant gas giant, could provide continuous internal heating that maintains geological activity, volcanism, hydrothermal systems, the recycling of nutrients and minerals that long-term complex chemistry might need. Some researchers have suggested that the most habitable environments in the universe might not be planets orbiting in habitable zones, but moons experiencing sustained tidal heating from a gas giant host. The energy source is internal and therefore not subject to the variability of a star's output. It runs on orbital mechanics, which is extremely stable on geological timescales. None of this is a claim that something lives on a moon of S1. To be completely clear, we do not know that S1 is real. We do not know that it has moons, and we have no evidence whatsoever of biology anywhere beyond Earth. What we have is a candidate gas giant in the habitable zone of the nearest Sun-like star, at the right mass range to host large moons, on an orbit consistent with having a dynamically eventful history that could have produced large companion worlds through capture or in situ formation. The scientific case for investigating this more deeply, for confirming S1 and then asking what orbits it, is completely solid. The existential speculation is optional, but I think it is worth doing, because if we never ask the question, we will certainly never find the answer. Part 18. Seasons of Extremes. Back to the orbit. An eccentricity of 0.4 is not extreme by exoplanet standards. We know of planets with eccentricities above 0.9, which put them on almost cometary orbits, but it is significant enough to create major seasonal variations in stellar flux. For a moon orbiting S1, the total stellar radiation received from Alpha Centauri A varies by roughly a factor of 5 between the most and least irradiated parts of S1's orbit. 5 times more energy arrives at peristron than at apastron. Is this fatal for habitability? Researchers have examined exactly this question, and the answer is more nuanced than you might expect. William Baines and others have modelled how eccentric orbits affect planetary climate, and what they consistently find is that climate is not just determined by instantaneous flux, it is determined by the time-averaged flux, the total energy received over a full orbital period, and by the buffering capacity of the planetary system. A moon with significant ocean coverage can absorb a large amount of heat during the warm phase of an eccentric orbit, and slowly release it during the cold phase, acting as a giant thermal reservoir. The temperature extremes are smoothed out by the thermal mass of the ocean. Modelling from Williams and Pollard, published in the early 2000s, showed that planets on moderately eccentric orbits can maintain habitable surface conditions even when they spend part of their orbit well outside the nominal habitable zone boundaries, as long as their time-average stellar flux falls within the habitable range, and they have sufficient surface water to buffer the temperature swings. For S1's orbital parameters, the time-average stellar flux received by a moon orbiting it would likely fall within the range permitting liquid water for at least a significant fraction of the orbit, depending on the exact semi-major axis. There would be extraordinary seasons, though. Near periastron, when S1 swings through the inner edge of the habitable zone, the lunar surface might experience conditions warmer than Earth's tropical regions, intense storms, elevated evaporation, a turbulent climate driven by rapid heating. Then, as S1 moves toward apastron, temperatures drop steadily over the course of months. Ice advances from the poles. The atmosphere thickens with condensation. Near apastron, surface temperatures in temperate regions might fall below 0 Celsius, though the thermal buffer of oceans would prevent a total freeze-over in most models. Then S1 begins its return toward periastron. The warmth returns, ice retreats, and the cycle begins again. All of this on a timescale of 2 to 3 years, fast enough to be biologically significant, slow enough to permit adaptation. Life on Earth has adapted to seasons. It has adapted to ice ages. It has adapted to periods of intense volcanism, periods of very low solar output, periods of high meteorite bombardment. Life is not fragile in the way we intuitively assume. It is extraordinarily resilient within its operating envelope, and the envelope itself is wider than we tend to think. Whether the climate extremes of Swan's eccentric orbit fall within an envelope that Earth-like chemistry could exploit, we honestly do not know, but we cannot rule it out, and the uncertainty alone is enough to make confirmation of S1 one of the most scientifically important events that could happen in the next decade. Part 19, The View from the Surface. Let me take you somewhere, not in the hypothetical future, not in the vague abstract. Let me take you to the surface of a moon orbiting S1 right now, 4.367 light-years from Earth, and let me describe what it would be like to stand there and look up. You're on a world with roughly Earth-like gravity, let us say the moon is about Earth's size, which is within the range of what is scientifically plausible. The sky above you is not the blue sky of Earth. If the atmosphere has a different composition, more methane, more nitrogen, less oxygen, it might scatter light differently, producing skies that shade from violet at the zenith to deep amber on the horizon. Or it might be similar to Earth's sky if the chemistry works out comparably. We do not know, but let us say it is clear enough to see. Above you, filling perhaps 30 degrees of sky, hangs S1. Not as a disk you see in passing, the way a moon hangs in Earth's daytime sky. As a presence. A planet the size of Jupiter occupies a portion of the sky that is genuinely large, genuinely imposing. You can see the cloud bands without any optical aid, parallel stripes of different colours running across the equator of the planet, yellows and ochres and whites, disrupted here and there by enormous storm systems the size of Earth's continents. The ring system, if S1 has one, and many gas giants do, catches the light from Alpha Centauri A and produces a shimmering arc across the sky, brighter on the sunlit side and fading into darkness where the planet's shadow falls across the rings. Alpha Centauri A itself hangs in that same sky. From roughly 1 to 2 astronomical units away, the star appears slightly larger and slightly brighter than our Sun appears from Earth. It is yellowish-white, warm, familiar. Your shadow falls sharp on the ground ahead of you. But there is a second shadow, softer and slightly offset. Alpha Centauri B, currently about 20 astronomical units from A, appears from your position on this moon as a small but distinctly visible disk, not as large as A, less intensely bright, but clearly present. On an overcast night, it would be the most visible astronomical object in the sky after S1 and A. During the day, at the right sun angles, it creates a secondary illumination that softens the shadows on one side, while A's light sharpens them on the other. This effect, the dual shadowing, would be visible to any being present on this surface. Every object, every geological feature, every creature that might theoretically move across this landscape would cast 2 shadows at most hours of the day. 2 shadows from 2 suns, of slightly different colours, one slightly yellower, one slightly more orange. On the horizon, visible at night clearly and perhaps faintly at dusk, is a reddish point that does not twinkle the way distant stars do. Proxima Centauri, the red dwarf companion, glows with a deep salmon colour. Too faint to illuminate anything, but bright enough to stand out against the stellar background. A navigational landmark, something you could steer by. 3 stars in the sky, 1 primary sun, 1 warm secondary, 1 distant red watch point, and a gas giant filling a significant portion of the hemisphere above. This is not a hypothetical future. The physics says this sky would exist right now on a moon orbiting S1 if S1 is real and if it has moons. The question of whether anything is looking up at it is unanswerable at our current level of technology. but the question of whether the sky itself exists will be answered in approximately 16 months. Part 20. The Pale Blue Dot, Inverted. In February 1990, as the Voyager 1 spacecraft was leaving the solar system at a distance of about 6 billion kilometers from Earth, Carl Sagan convinced NASA to turn the camera around and take one last photograph of home. The resulting image showed Earth as a tiny point of light, barely a pixel, suspended in a beam of scattered sunlight against the darkness of space. Sagan called it the Pale Blue Dot. He wrote about it with extraordinary humility and precision, noting that everything humanity had ever known, every king and peasant, every scientist and soldier, every creator and destroyer of civilization, had lived out their lives on this mote of dust suspended in a sunbeam. That image inverted the typical perspective of astronomy. Instead of looking outward at distant things, we were looking back at ourselves from outside. The Earth, seen from distance, was anonymous, a point, indistinguishable from the countless other points scattered across the black. Now consider S1. If it is real, if a gas giant is genuinely sitting there, 1 to 2 astronomical units from Alpha Centauri A, 4.367 light-years away, then our telescopes have just done the inverse of what Voyager 1 did. We have not looked at ourselves from outside. We have looked at another dot from the inside. We have observed a photon, a faint thermal infrared photon, that travelled 4 1/3 light-years from another solar system and landed on JWST's detector, and that photon may have come from a gas giant in the habitable zone of the nearest sun-like star. It may have originated in some tiny fraction from the thermal emission of a world that we will one day talk about the way Sagan talked about Earth. That is the inversion. We started as the pale blue dot, tiny, anonymous, a pixel in someone else's sky. If S1 is real, we have just seen another pixel. We have not resolved it into a world. We cannot see its surface or its clouds or its storms or its moons. We have seen a faint smear of heat in a data array after a 45-minute exposure through a coronagraph around the nearest sun-like star. But it is a smear of heat in exactly the right place, at exactly the right brightness, to be a gas giant in the habitable zone of our closest stellar neighbour. And the history of science is full of moments where a faint smear in a data array eventually became the most important thing anyone ever measured. August 2026 is when we find out whether this is one of those moments. Part 21. The Prediction. Let me be very precise about what the prediction for August 2026 actually is, and why it carries as much weight as it does. Because predictions in science are not like predictions in everyday life. When your friend predicts it will rain this weekend, they are making a guess based on vibes and maybe a quick glance at a weather app. When a scientist makes a prediction in a peer-reviewed paper, they are doing something categorically different. A scientific prediction is not a guess. It is a specific, quantified, falsifiable statement about what the universe will do under certain conditions, derived from a formal model that can be written down in equations and checked by anyone with the right training and the right data. And a prediction that comes before the observation, rather than being fitted to the observation after the fact, is the gold standard of scientific evidence. This distinction matters enormously, because the history of science is littered with beautiful explanations that were constructed to match existing observations. Those explanations might be true, but they could also be elaborate coincidences. The only way to know the difference is to put the explanation to a test it could fail, to make it stake its reputation on a new observation that has not happened yet, and then go check. That is exactly what the S1 team has done. Let me walk you through how the prediction was actually built, because the engineering of it is itself a small masterpiece of scientific reasoning. The orbital models used to generate the August 2026 prediction were constructed from a surprisingly short list of inputs, but each one is doing a tremendous amount of work. First, the team used the measured position and brightness of S1 in August 2024, where exactly the candidate appeared on the detector, how bright it was, at what angle from the star. That single measurement by itself is not enough to pin down an orbit. A planet at a given position could be moving in countless directions, at countless speeds, along countless possible trajectories. You need more constraints. The second input is the non-detections in February 2025 and April 2025. This is where things get genuinely clever. A non-detection sounds like no information at all, nothing was seen, so what can you possibly learn from nothing? But in this case, nothing is actually a very specific statement. It means that whatever S1 is, it was not in any of the positions where JWST would have been sensitive enough to see it at those two epochs. That rules out entire families of orbits. Any orbit that would have placed S1 in a high sensitivity region of the detector in February or April 2025 is immediately eliminated. The non-detections are not gaps in the data. They are constraints. They are the universe saying, not here and not here either. And every not here chips away at the space of possible orbits the planet can be on. The third input is the measured sensitivity maps of the JWST-MIRI, coronagraphic observations of Alpha Centauri A. These maps characterize, pixel by pixel, which positions on the sky around the star can be detected at which confidence levels. They are not uniform. Closer to the star, the residual glare of scattered light makes detection nearly impossible. Certain angular directions are worse than others because of how diffraction patterns fall across the detector and how light from the binary companion, Alpha Centauri B, contaminates specific regions. The sensitivity maps are essentially a topographical chart of the telescope's vision around this particular star, a map of the places where we can see clearly, the places where we can barely see, and the places where we are effectively blind. Without these maps, a non-detection tells you nothing. With them, a non-detection becomes a precise statement. The planet is not in any of the green zones, but it could still be hiding in the red zones. The fourth input is the known physical properties of Alpha Centauri A itself, its distance, its mass, its luminosity. These are the numbers that anchor the whole calculation to reality. Because Kepler's laws, written down 400 years ago by a guy staring at Mars data without even a telescope, tell us exactly how an object orbits around another object of a given mass. If you know the mass of the star, you know how fast a planet at any given distance has to move. If you know the distance to the system, you can translate angular separations on the sky into physical distances in astronomical units. These are not guesses. They are among the most precisely measured quantities in astronomy. Alpha Centauri A's distance is known to something like 1 part in 10,000. Its mass is known to better than 1%. These numbers feed into the orbital calculation as hard constraints. From those 4 inputs, 1 detection, 2 non-detections, a sensitivity map, and the stellar properties, the team did something that would have been unthinkable a generation ago. They ran millions of simulated orbital trajectories, literally millions, every combination of semi-major axis, eccentricity, orbital inclination, longitude of periastron, and initial orbital phase that is physically consistent with the observations was tested. Each simulated orbit was essentially a hypothesis. What if the planet's orbit looked like this? For each hypothesis, the simulation calculated where the planet would have been in August 2024, in February 2025, and in April 2025. Most of those hypothetical orbits were immediately rejected because they predicted the planet should have been visible in February or April, in positions that the sensitivity map says JWST would have seen it. Those orbits are inconsistent with the observed non-detections. They are thrown out. What survives is a constrained family of orbits, a smaller, more precise set of trajectories that simultaneously explain visibility in August 2024, invisibility in February 2025, and invisibility in April 2025. No single orbit. A family. Because 3 data points is not enough to uniquely specify an orbit in 6-dimensional parameter space. But a family is much, much more useful than no constraints at all. And here is where the predictive power emerges. When you project that family of orbits forward in time to August 2026, you get a distribution of predicted positions. Not a single point. The genuine uncertainty is preserved, because the data does not justify claiming more precision than you actually have. But the distribution is localized. It does not smear across the entire sky around Alpha Centauri A. It concentrates in a specific region of the image plane, at a specific angular separation, and a specific position angle from the star, at a specific brightness consistent with S1's thermal emission, at 15.5 microns. The prediction has a shape and a place. Now here is the part that keeps me up at night thinking about it. The JWST-MIRI coronagraphic mode is sensitive enough to detect S1 at that predicted position, if it is there. The sensitivity maps, the same ones used to generate the prediction, show that the predicted reappearance zone falls in a region of relatively low contamination from Alpha Centauri B's scattered light. That is not a coincidence. That is actually why the orbital models put S1 there. The previous detection happened in a similar clean zone, and the non-detections are consistent with the planet having swept through a noisier, more contaminated region of the image plane in the months between. The geometry works out. The prediction is internally consistent. Everything the model says about why the planet appeared, why it disappeared, and why it should reappear fits together in a single coherent story. If S1 reappears in August 2026 at the predicted location, at roughly the right brightness, in roughly the right spot behaving the way a real planet should behave after 2 years of orbital motion, the probability of that being a coincidence is extremely small. Not zero. Science never gives you zero. There is always some tiny residual chance that the universe has conspired to fool you with an unusually persistent, unusually well-positioned noise artifact. But that probability is small enough to justify a confident shift from the word candidate to the word confirmed. And that single word change, candidate to confirmed, would be felt far beyond the technical community of exoplanet astronomers. It would be the moment the nearest sun-like star to our own officially joined the list of places we know have planets. Not hypothetical planets, not candidate planets. A real, imaged, catalogued world, 4.367 light-years away, waiting for us to keep looking. Part 22. What confirmation looks like. Let us play out the scenario in which the signal comes back, because this is the moment everything has been building toward. This is the payoff to the careful work, the restraint, the patient waiting, the years of modelling and simulation and calibration. This is the moment when the word candidate quietly dies, and the word confirmed takes its place. August 2026. The JWST observations execute, whether scheduled ahead of time as part of a previously approved cycle, or triggered by an approved director's discretionary program that jumps the line for exactly this kind of high-stakes follow-up. The telescope, parked 1.5 million kilometers from Earth, at the L2 gravitational balance point, slews smoothly into position. Its enormous gold-coated hexagonal mirror orients itself toward the nearest sun-like star in the galaxy. The chronograph activates, the precision mask sliding into the beam path to block the blinding central glare of Alpha Centauri A, MIRI, the mid-infrared instrument, the one that sees heat rather than visible light, begins integrating. 45-minute exposures, one after another, photons accumulating patiently on the detector in the thermal infrared, where warm gas giants glow faintly against the cold of space. The data comes down to Earth over the next hours and days, compressed and transmitted through the Deep Space Network, eventually arriving at the Space Telescope Science Institute in Baltimore, where the raw frames are processed into calibrated science products. The analysis pipeline runs. PCA-KLIP subtraction gets applied. The stellar point spread function is modelled, characterised and mathematically removed. Whatever sits in the residuals, whatever remains after the starlight has been peeled away, emerges for inspection. And there, at the predicted position, within the predicted position angle range, at a flux consistent with the August 2024 detection, is S1. Not louder, not different. Just exactly what the model said should be there, almost exactly where they said it should be, glowing faintly at roughly the brightness they said it should glow at. Because that is what a real planet does. It shows up where orbital mechanics says it should show up. It does not drift randomly. It does not change its thermal signature dramatically from epoch to epoch. It behaves according to laws that were written down 4 centuries ago by a man who never saw a telescope better than a toy by modern standards. It obeys Kepler. What happens next is not a press conference, at least not immediately. This is something the general public often misunderstands about how science actually works in real time. A single data point, no matter how exciting, does not trigger immediate announcements. The first thing that happens is internal verification, a careful, almost obsessive process of trying to destroy your own discovery. The team checks the detection against the most recent sensitivity maps to make sure the position is not in a region where a known systematic effect could produce a false signal. They check whether the position is within the predicted zone, and if so, how close to the central prediction it falls. They check the brightness against what the thermal emission model predicts. They run the KLIP analysis multiple times with different parameter sets, different numbers of principal components retained, different reference libraries, different aggressiveness settings, to confirm the signal is robust to changes in the reduction approach. Because if a signal only appears with one specific reduction configuration and disappears when you change the parameters, that is not a planet. That is a ghost. They look for any possible instrumental artifact that could explain the detection. Detector persistence, where bright sources leave lingering afterimages on the pixels. Cosmic ray hits, where high-energy particles slamming into the detector create bright spots that can masquerade as point sources. Scattered light from other sources in or near the field, Alpha Centauri B, background stars, even faint sunlight scattering into the telescope if the orientation is wrong. Every possible explanation other than a real planet gets interrogated and either ruled out or flagged for further investigation. This process takes weeks, possibly months. Careful science is not fast science, and the team has every reason to be maximally careful, because this is the detection their careers will be remembered for. Nobody wants to be the person who announced the closest exoplanet in human history, and then had to retract it 6 months later. The memory of Alpha Centauri BB is still too fresh, still too painful, still too instructive. And then, assuming the signal holds up to scrutiny, assuming nothing can explain it except a genuine orbiting planet, a paper is submitted to a scientific journal. Probably Nature, possibly Science, possibly one of the top-tier astrophysics journals. In parallel, or perhaps before submission, results may be shared with the broader community through a preprint posted on the Archive, the online repository that serves as the astrophysics equivalent of a draft posted publicly, before formal peer review. This is standard practice now, and it has been for years. It means the community knows about the detection before the paper is formally published, which allows other researchers to begin their own follow-up work immediately, rather than waiting 6 months for publication to run its course. The impact on subsequent observations would be immediate. Every major observatory on Earth and in space with coronagraphic capability would begin considering whether it can contribute a follow-up measurement. Telescope time proposals would be rewritten overnight. Directors' discretionary time requests would flood in. The extremely large telescope, if it is in its early operations phase by 2026, as currently projected from its construction timeline in the Atacama Desert of Chile, would immediately become the hottest target in the world. The ELT's primary mirror is 39 meters across, almost 4 times the diameter of JWST's mirror, collecting roughly 16 times the light, and its coronagraphic instruments will have diffraction-limited resolution that JWST cannot match at shorter wavelengths. ELT observing at near-infrared wavelengths, and potentially even in the visible, could detect S1's reflected starlight from Alpha Centauri A, providing colour information that JWST cannot access. The contrast between thermal emission at 15.5 microns and reflected light at shorter wavelengths, is sensitive to cloud properties, atmospheric chemistry, the presence of water vapor or methane or ammonia features in the planet's atmosphere, and potentially even surface conditions if clouds break. Gaia's Astrometric Data Archive, covering the full operational lifetime of the European Space Agency's precision position measuring satellite, would be reanalyzed almost immediately, with the specific goal of detecting the reflex motion of Alpha Centauri A caused by a gas giant companion with the now confirmed orbital parameters. The signal would be tiny, genuinely microscopic. The gravitational tug of a 90 to 150 Earth mass planet at 1 to 2 astronomical units on a star with Alpha Centauri A's mass would cause a reflex wobble with an amplitude of microarc seconds. That is not a typo. Microarc seconds, a millionth of a second of arc, an angle so small it barely exists as a human concept. But Gaia's precision is in exactly this range, and with many years of baseline data already accumulated, a tentative astrometric signal might be extractable once the analysts know precisely what period and phase to search for. Confirmation via a completely independent method, using physics that has nothing in common with coronagraphic imaging, would transform the detection from well-established to ironclad. Radial velocity programs at high-precision spectrographs, espresso at the Very Large Telescope in Chile, for example, or HARPS at La Silla, or the newer generation of extreme precision instruments now coming online, would redouble efforts to find the corresponding Doppler wobble in Alpha Centauri A's spectrum. A gas giant at 1 to 2 astronomical units would induce a radial velocity semi-amplitude of perhaps 10 to 30 meters per second, which is well within the capabilities of modern spectrographs. The historical challenge has always been the stellar activity of Alpha Centauri A, which produces its own intrinsic radial velocity variations, magnetic spots, convective patterns, acoustic oscillations, that can swamp a planetary signal if you do not know what frequency to look for. But with a known orbital period and phase from the imaging confirmation, the planetary signal becomes dramatically easier to extract from the activity noise. You know what you're looking for, you know when it should peak and when it should trough. That changes everything about the analysis. Within a year or two of the August 2026 confirmation, if it happens, S1 would become the best characterized exoplanet in the entire direct imaging sample. Mass from astrometry, orbital parameters from imaging, atmospheric hints from multi-wavelength photometry, radial velocity amplitude from spectroscopy. 4 completely independent lines of evidence converging on the same object, each refining our understanding in its own way. It would be the only directly imaged planet we know orbits a sun-like star at a distance relevant to habitability questions. Not habitable itself, S1 is a gas giant, and gas giants do not host life as we understand it, but sitting right there, in the region where liquid water could exist on a solid surface, around a star essentially identical in type to our own, and it would immediately become the primary science target for the proposed Habitable Worlds Observatory, the next-generation NASA Space Telescope currently in early design phase, explicitly built to image Earth-like planets around nearby Sun-like stars. The existence of a confirmed gas giant in the Alpha Centauri A system would tell HWO exactly where to look for smaller, rockier, more Earth-like companions. It would shift the entire question from is there a planet next to Alpha Centauri A to what kind of planet is it, and what does it tell us about whether Earth-like worlds might also exist in this system? That second question is a fundamentally different question. It assumes the planet is real. It takes the existence of worlds next door as given, and it starts asking what else might be there. Part 23. What if it doesn't? But we have to be honest with ourselves here, because the honest accounting of Alpha Centauri's history demands it. We have been burned before, more than once, and if I tell you the story of S1 without also telling you the story of what it looks like when the signal does not come back, I am not being a fair guide. I am being a cheerleader, and that is not what this channel is for, so let us walk through the other possibility. The darker one, the one that has happened before, around this very star, more times than anyone who cares about this system likes to remember. What if August 2026 comes, the observations run, the analysis completes, and there is nothing? No signal, no faint point source at the predicted position, no reappearance, just a sky next to Alpha Centauri A that looks exactly the same as it did in February and April 2025, clean, empty, below the detection threshold everywhere the orbital model said the planet should be. The KLIP pipeline runs, the residuals are inspected, and where S1 should have been, where millions of simulated orbits all said it ought to be glowing faintly at 15.5 microns, there is simply nothing. A flat noise floor, the kind of clean, quiet image plane that, in any other context, would be reassuring. But in this context, it is devastating. The first interpretation would be statistical rather than final, because even a non-detection is not necessarily a refutation. If S1 was real but simply not detectable in the 3-observation window covered so far, if the planet's orbit is slightly different from the best-fit orbital models, placing it in a lower sensitivity zone even at the August 2026 epoch, then a non-detection would not definitively disprove it. The prediction would have failed in a specific technical sense, but orbital models built from only 3 data points carry real uncertainty. The predicted reappearance zone, while localized, is not a single pixel. It is a distribution of possibilities, and some of those possibilities include orbital configurations where the planet is again just below the edge of what JWST can see. A somewhat broader non-detection, one that happens inside the predicted zone but leaves some plausible orbital solutions still unchecked, would leave the candidate alive but significantly weakened. The team would go back to the modelling. They would use the new non-detection as another constraint on the orbit, just as they used the February and April 2025 non-detections the first time around. They would refine the predicted reappearance window for the next opportunity, perhaps 1 or 2 years later, and another observation would be scheduled, and the waiting would begin again. Alpha Centauri has a way of demanding patience. It teaches you that the universe does not operate on the timescale of human curiosity. However, and this is the harder scenario, if the non-detection is complete, meaning JWST achieves its full designed sensitivity across the entire predicted zone, and still sees nothing at the noise level required to detect a source as bright as S1 was in August 2024, then a genuine failure to detect would substantially increase the probability that the original signal was a false positive. The simplest explanation that fits a confirmed detection followed by a confirmed non-detection in the predicted reappearance location is not a missed orbital phase. It is not a slightly wrong orbital model. It is that the original detection was not a planet at all. It was a PSF artifact, structured noise generated by the complex interaction of residual starlight, detector imperfections, and the specific thermal state of the telescope during that one 45-minute exposure session. It happened to sit at the right position, at the right brightness on one particular observation, and then it was simply absent on subsequent observations because the noise pattern itself shifted. No orbital motion, no hiding behind a contamination zone. Just a ghost in the pixels that looked for one night exactly like what we wanted to see. This would not be a failure of JWST. The telescope would have performed flawlessly. It would not be a failure of the team who detected and analysed S1. They followed every appropriate protocol, labelled the finding as a candidate rather than a confirmation, published their orbital models transparently, and submitted their prediction to the most rigorous possible test. It would be science working exactly as it should. A candidate is detected, a prediction is made, the prediction is tested, the test fails, the candidate is retired. That is the full clean cycle of how scientific claims are either strengthened into knowledge or quietly removed from consideration. There is no scandal in this outcome. There is no embarrassment. There is only the ordinary, unglamorous process of knowledge correcting itself in real time, and crucially, the non-detection itself would be scientifically valuable information. This is something people outside of science often miss, because non-detections do not make headlines. But a confirmed non-detection at JWST's sensitivity limits around Alpha Centauri A, combined with the orbital constraints from the S1 claim, would place meaningful upper bounds on the mass and temperature of any planet that could exist in the 1 to 2 astronomical unit region around the star. That kind of statement, there is no gas giant above this mass threshold at these orbital distances, is actually an important constraint on planet formation models in binary star environments. We still do not fully understand how planets form and survive around stars in close binary systems like Alpha Centauri A and B. Theory predicts certain outcomes. Observation tests them. A non-detection of S1 would not be empty. It would be a data point. It would tell us that whatever Alpha Centauri A has around it, it does not have a warm gas giant brighter than roughly 3 millijanskis at 15.5 microns between 1 and 2 astronomical units. That might sound like a narrow technical statement, but for theorists trying to model how gas giants migrate, how binary stellar companions perturb planetary orbits, and how often systems like this retain their giant planets over billions of years, it is useful. It is real information. The search for S1 would have paid scientific dividends even in failing to find it. The scientific community would not be devastated by a non-detection. Disappointed, certainly. Some careers would take a harder bend than the authors hoped. Some grad students who bet their dissertations on S1 being real would need to pivot. There would be quiet, difficult conversations at conferences, but the machinery of science is built for this exact outcome. Non-detections get published. Limits get recorded in the literature. Theoretical papers get written that cite the null result as a constraint, and the search continues, always. The next generation of coronagraphs, on the extremely large telescope, on the Habitable Worlds Observatory, on whatever successor space telescope NASA and its international partners eventually build, will push deeper. They will see fainter sources. They will achieve better inner working angles. They will resolve regions of the sky that JWST can only approach at the edge of its capability. Eventually, if anything is actually there around Alpha Centauri A, it will be found. The null result from a JWST non-detection in 2026 would just mean that the planets in this system, if they exist, are smaller, cooler, or closer in than the S1 candidate suggested. It would tell us we need sharper eyes, not that we should stop looking. What a non-detection would also do, though, and this is the softer, more human observation I want to leave you with, is reinforce once more the peculiar difficulty and the peculiar temptation of Alpha Centauri itself. This is the nearest sun-like star to our sun. Of course we keep looking. Of course every marginal signal gets attention, and hope gets invested, and careers get attached. And of course that hope is, with painful regularity, disappointed. The history of this system is a history of humanity's desperate desire for a neighbour running headlong into the universe's serene indifference to what we want. Alpha Centauri BB in 2012, Proxima C in 2019 still contested, and possibly, if the numbers break the wrong way, S1 in August 2026. A non-detection would be the latest chapter in that long bruising story, but it would not be the last chapter. Because we will keep looking. We cannot help it. The star is simply too close. The question is simply too important. And the human need to know if we're actually alone in this stellar neighbourhood is too fundamental to give up just because one specific candidate did not survive its reappearance test. The search continues because the search is who we are. Part 24. The first real destination. Let me end with something that I think deserves more attention than it usually gets in discussions of exoplanet astronomy. Because we talk a great deal about discovering other worlds, cataloguing their properties, characterizing their atmospheres and temperatures and masses. But there is a harder question lurking underneath all of that. What do we actually do with the knowledge? In the last decade, a project called Breakthrough Starshot has been actively developing a concept for interstellar travel. Not theoretical interstellar travel, not vague horizon of the century interstellar travel, but an engineering roadmap for sending spacecraft to Alpha Centauri within our lifetimes, or the lifetimes of our children. The concept involves a fleet of tiny gram-scale laser sail probes, each one about the size of a postage stamp, accelerated to roughly 20% of the speed of light by an array of ground-based lasers. At 20% the speed of light, 60,000 kilometers per second, the journey to Alpha Centauri takes approximately 22 years. To be clear, this is not a mission that lands anywhere. At 20% of light speed, the probes would pass through the Alpha Centauri system in a matter of hours, taking pictures and measurements as they streak past. You cannot decelerate a laser sail without something to push against at the destination, and the current concept does not include a deceleration mechanism. These would be flyby probes, the first humans to know that a Voyager-class spacecraft is passing through the nearest stellar system, 4 light-years away, taking pictures in real time. If S1 is confirmed, if there is genuinely a gas giant in the habitable zone of Alpha Centauri A, the scientific case for breakthrough starshot or a mission like it becomes dramatically stronger. You would know what to look at, you would know approximately where to aim. You could optimize the instruments on the probe for the specific characteristics of S1 and its potential moons. The difference between flying blindly through a stellar system and flying through a stellar system where you know a potentially habitable region exists is the difference between an expedition to an unmapped wilderness and a targeted exploration of a known location. There is also the Ptolemy mission, a proposed small spacecraft designed to measure the astrometric wobble of Alpha Centauri A and B with extraordinary precision, hunting for the gravitational signatures of planets through the tiny deflections they induce in the stars' proper motions across the sky. Ptolemy would provide an independent astrometry-based detection method entirely complementary to JWST's imaging approach. If S1 is real, Ptolemy should eventually detect the astrometric signal of a gas giant at 1 to 2 astronomical units from Alpha Centauri A, and if it does, the 2 completely independent detection methods converging on the same object would constitute one of the most compelling confirmations in the history of exoplanet science. Further out in the timeline, the proposed Habitable Worlds Observatory, a large space chronograph successor to JWST, currently in early study phase at NASA, is explicitly designed to directly image Earth-like planets around nearby Sun-like stars in reflected starlight. Alpha Centauri A is one of its primary targets. If S1 is confirmed as a gas giant in the habitable zone, and if HWO operates in the 2030s or beyond, the mission would be able to probe the inner regions of the Alpha Centauri A system for smaller, rocky planets at even smaller orbital separations, the kind of planets where biology as we know it might actually exist. A confirmed gas giant at 1 to 2 astronomical units would tell us a great deal about the dynamical history of the inner system, potentially informing models of where rocky planet formation was possible. 4.367 light-years. That number means something different today than it did 5 years ago. 5 years ago, it was a distance, a measure of cosmic proximity that was practically useful for nothing except marking Alpha Centauri as the nearest thing on a list. Today, there is a candidate planet at that distance, a faint smear of thermal emission in JWST data that might be a gas giant, might be orbiting in the habitable zone of the nearest Sun-like star, and will be tested against a specific prediction within the next year and a half. If it passes that test, if the signal comes back in August 2026 at the predicted position, then 4.367 light-years becomes something new. It becomes a destination. Not a tourist destination, not a reachable destination in any near-term human sense, but a destination in the most profound meaning of the word, a place. Not a point of light, not a data coordinate, a place that exists with worlds orbiting it, with a sky above those worlds, with perhaps weather and geology and chemistry and heat sources capable of sustaining complexity. A place that our probes, accelerated by light, might reach within 20-odd years. A place that our descendants might one day know better than we know any place beyond our own solar system. We have been staring at Alpha Centauri for centuries. Every astronomer in the southern hemisphere has seen it as the brighter of the two pointer stars to the Southern Cross, a familiar, brilliant constant in the night sky. For most of human history, it was simply a beautiful point of light. Then we learned it was a system of 3 stars. Then we learned it was the nearest stellar system to our own. Then we learned it was the closest sun-like star. And now, tantalizing and uncertain and subject to a test that will run in August 2026, we may have found that it is also the location of the nearest gas giant in the habitable zone of any star we have ever observed. Think about what it means to be the first generation that might know the answer to this. Every human who ever lived before us, every philosopher who wondered about other worlds, every astronomer who mapped the sky, every science fiction writer who imagined journeys to the stars, none of them knew whether there was anything orbiting Alpha Centauri. Not a clue, not a hint. Complete, absolute silence from the nearest stellar neighbour. We are the first generation with the technology to actually ask the question and get a real answer. And the answer might be yes. We might be looking at it right now, in the data, sitting at 3.5 millijanskis at 15.5 microns, labelled S1 because the scientists who found it were careful enough to know that discovery is not the same as detection. 1 observation epoch, 2 non-detections, millions of orbital simulations, 1 prediction, 16 months to find out. The universe has been making us wait for this answer for as long as we have had the question. In the span of cosmic time, stars that live for billions of years, galaxies that take hundreds of millions of years to rotate once, 16 months is less than a breath. But for us, right now, watching this unfold, knowing that a specific calendar month will either transform our understanding of our neighbourhood or quietly add another name to the graveyard of Alpha Centauri hopes, 16 months feels like a long time, and somewhere, 4.367 light-years away, under a sky with 3 suns casting layered shadows across whatever terrain might exist, on whatever moon might orbit, whatever gas giant might be drifting through the habitable zone of the nearest star to our sun, the universe is not waiting. It is simply being what it has always been. The question has always been whether we are paying close enough attention to notice. We think we finally might be.